NVidia AI endpoints callbacks. Description: LangChain callbacks for NVIDIA AI endpoints are a powerful tool for monitoring and debugging your LLM applications. They allow you to capture detailed information about every step of the execution process, including the input prompts, model responses, execution times, and any errors encountered. This information can be used to improve the performance and reliability of your applications, identify potential bottlenecks, and track the progress of your development efforts. Inputs: prompt: the user-provided input text that triggers the LLM's response. Model input: the processed and formatted version of the prompt that is actually sent to the LLM. Model for processing: this may include additional context, instructions, or formatting. Model output: the raw output generated by the LLM model in response to the input. This is often in a textual format, but may also include structured data or other representations. Outputs: callback events: these are specific events triggered during the execution of the LLM application, such as the start of a chain, the completion of a step, or the handling of an error. Each event includes details about the specific action taken, the time it occurred, and any relevant data associated with it. Logs: a chronological record of all the events and actions that occurred during the execution of the application. This can be used to trace the flow of data and identify any issues that may have occurred. Metrics: quantitative measures of the performance and efficiency of the LLM application, such as the execution time, the number of tokens processed, and the memory usage. Steps: initialization: the callback is instantiated and configured with the desired settings, such as the logging level and the data to be captured. Event handling: the callback listens for events triggered by the LLM application and processes them accordingly. Data collection: the callback collects relevant information about the events, such as the input prompt, the model response, the execution time, and any errors encountered. Data storage: the collected data is stored in a specified location, such as a file, a database, or a cloud storage service. Metrics: execution time: the time taken by the LLM model to generate a response to a given prompt. This metric can be used to assess the efficiency of the model and identify potential performance bottlenecks. Token count: the number of tokens processed by the LLM model during the execution of a application. This metric can be used to estimate the computational cost of running the model and identify any potential resource limitations. Memory usage: the amount of memory consumed by the LLM model and the application during execution. This metric can be used to identify potential memory leaks or excessive memory usage. Visualization plots: execution time histogram: a plot showing the distribution of execution times for different prompts or tasks. This can help identify outliers and understand the overall performance of the application. Token count scatter plot: a scatter plot showing the relationship between the length of the input prompt and the number of tokens processed. This can help assess the scaling behavior of the LLM model. Memory usage trend chart: a line chart showing the memory usage over time during the execution of the application. This can help identify potential memory leaks or spikes in usage. Fine-tune parameters: logging level controls the verbosity of the callback's output, allowing you to adjust the amount of information captured. Data storage location specifies where the collected data is stored, such as a file, a database, or a cloud storage service. Event filtering allows you to select specific events to capture, filtering out irrelevant information and reducing the amount of data collected. Uncertainty methods: Confidence score, a measure of the model's certainty in its response, based on the internal workings of the LLM. Ensemble prediction, combining the predictions of multiple models to produce a more robust and accurate result. Bayesian inference, a statistical approach to incorporating uncertainty and prior knowledge into the model's predictions. Challenges and fixes. Challenge 1: overwhelming amount of data. Capturing every detail can lead to a large amount of data that is difficult to analyze and manage. Sample use case that resulted in Challenge 1: running a large-scale LLM application with many requests and detailed logging enabled. Fixes to Challenge 1: implement data filtering mechanisms to capture only the most relevant information. Use aggregation techniques to summarize data into meaningful metrics. Utilize data compression methods to reduce storage space. Challenge 2: performance overhead. Excessive data collection and processing can impact the performance of the LLM application. Sample use case that resulted in Challenge 2: using verbose logging and data storage mechanisms on a resource-constrained device. Fixes to Challenge 2: optimize the callback implementation for efficiency. Leverage asynchronous processing to reduce blocking operations. Use lightweight data storage mechanisms. Challenge 3: integration with existing frameworks. Integrating callbacks with existing LLM frameworks may require modifications or custom implementations. Sample use case that resulted in Challenge 3: using a third-party LLM framework that does not natively support the desired callback functionalities. Fixes to Challenge 3: develop custom wrappers or adapters to bridge the gap between the callback and the LLM framework. Utilize existing integration libraries or plugins. Seek support from the framework maintainers. Challenge 4: security concerns. Data collected by callbacks can contain sensitive information, raising security concerns. Sample use case that resulted in Challenge 4: using callbacks to capture private user data or sensitive prompts in an LLM application. Fixes to Challenge 4: implement strong access control mechanisms to limit access to collected data. Use encryption techniques to secure data in transit and at rest. Follow best practices for data privacy and security. NVidia AI endpoints callbacks usage. Callback handler. Description: the usage callback handler is a powerful tool for tracking and analyzing the usage of your LangChain applications that use NVidia AI endpoints. It provides detailed insights into how your applications are interacting with the endpoints, allowing you to optimize performance, understand resource consumption, and identify potential issues. Inputs. Requests. This input captures every request sent to the NVidia AI endpoint from your LangChain application. It includes information like the model name, input prompt, request parameters, and the timestamp. Responses. This input captures the responses received from the NVidia AI endpoint. It includes the model output, response time, and any error messages. Outputs. Usage statistics. The callback handler aggregates all requests and responses to generate comprehensive usage statistics. This includes metrics like the total number of requests, average response time, most frequently used models, and peak resource utilization. Usage logs. The callback handler maintains detailed logs of all interactions with the NVidia AI endpoints, providing a complete history of your application's usage. Steps. Request handling. The callback handler intercepts each request made by your LangChain application to the NVidia AI endpoint. It gathers all relevant data, including the model name, input prompt, request parameters, and the timestamp. Response handling. The callback handler intercepts the response received from the NVidia AI endpoint, It records the output, response time, and any error messages. Data aggregation. The callback handler aggregates the collected request and response data to generate comprehensive usage statistics. This includes calculating average response times, identifying frequently used models, and tracking resource utilization over time. Logging. The callback handler writes the collected data to a log file, providing a detailed history of your application's interactions with the NVidia AI endpoints. Metrics. Total requests tracks the total number of requests sent to the NVidia AI endpoints. Average response time calculates the average time taken by the NVidia AI endpoints to respond to requests. Peak resource utilization monitors the peak resource utilization, e.g., CPU, memory during endpoint interactions. Visualization plots. Request count over time. A time series plot showing the number of requests made to the NVIDIA AI endpoints over a specified period. Response time distribution. A histogram showing the distribution of response times from the NVIDIA AI endpoints. Resource utilization heat map. A heat map visualizing the resource utilization, e.g., CPU, memory during endpoint interactions over time. Fine-tune parameters. Logging level. This parameter allows you to control the verbosity of the logs generated by the callback handler. Data retention period. This parameter defines how long the callback handler stores usage data. You can set it to retain data for a specific duration or indefinitely. Uncertainty methods. Confidence scores. The callback handler can be extended to capture confidence scores provided by the NVIDIA AI endpoint models, allowing you to analyze the uncertainty of model predictions. Error analysis. The callback handler can be configured to track and analyze error messages returned by the NVIDIA AI endpoints, helping you identify potential issues or biases in your application. Challenges and fixes. Challenge 1. Limited insights into model performance. The callback handler might not provide detailed insights into the performance of individual models. Sample use case. Your application uses multiple NVIDIA AI endpoints, and you want to understand the performance of each model separately. Fixes. You can extend the callback handler to capture and analyze model-specific metrics like accuracy, precision, recall, and F1 score, providing a deeper understanding of model performance. Challenge 2. Difficulty in identifying bottlenecks. Analyzing the usage data alone might not be sufficient to pinpoint performance bottlenecks in your application. Sample use case. Your application experiences slow response times, and you need to identify the source of the bottleneck. Fixes. You can integrate the callback handler with profiling tools to capture detailed performance metrics, allowing you to identify areas of inefficiency in your application or the NVIDIA AI endpoint. Infrastructure. LangChain NVIDIA AI endpoints callbacks get token cost for model. Description. The get token cost for model callback in LangChain's NVIDIA AI endpoints integration is used to estimate the cost associated with using a specific language model for a given prompt. It leverages the token count function from the LangChain LLMS base module to determine the number of tokens in the prompt and then applies pricing information provided by the NVIDIA AI endpoints service to calculate the cost. Inputs. Prompt. The text input provided to the language model. Model name. The name of the language model being used. Outputs. Token count. The number of tokens present in the input prompt. Cost estimate. The estimated cost of using the specified language model for processing the provided prompt. Steps. The callback first extracts the model name in prompt from the input. It then uses the token count function from LangChain LLMS base to determine the number of tokens in the prompt. The callback retrieves pricing information for the specified model from the NVIDIA AI endpoints service. This information includes cost per token. Finally, the callback multiplies the token count by the cost per token to calculate the estimated cost of using the language model. Metrics. Token count. This metric provides insights into the complexity of the input prompt and its potential impact on the model's processing time and cost. Cost estimate. This metric is crucial for budgeting and understanding the financial implications of using specific language models for different tasks. Visualization plots. Token count distribution. This plot visualizes the distribution of token counts across different prompts, helping identify patterns and potential outliers. Cost estimates per model. A bar chart comparing cost estimates for different language models can help users choose the most cost-effective option for their specific needs. Fine-tune parameters. None. Uncertainty methods. None. Challenges and fixes. Challenge 1. Inaccurate cost estimates due to variations in tokenization methods between different language models. Sample use case that resulted in challenge 1. A user using a different language model for a similar task may experience significant differences in cost estimates due to variations in how models tokenize text. Fixes to challenge 1. The callback could be extended to support different tokenization methods and incorporate model-specific pricing information to improve accuracy. Challenge 2. Difficulty in estimating costs for complex tasks involving multiple interactions with the language model. Sample use case that resulted in challenge 2. If a task requires multiple rounds of interaction with a language model, it becomes challenging to accurately estimate the total cost using just the initial prompt. Fixes to challenge 2. Implementing a mechanism to track the token usage across multiple interactions and providing cumulative cost estimates can address this challenge. NVidia AI endpoints callbacks. Get usage callback. Description. The get usage callback function is a callback function provided by LangChain that allows you to track the usage of an NVIDIA AI endpoint. It's particularly useful for monitoring costs and understanding the usage patterns of your AI applications. Inputs. Endpoint name. The name of the NVIDIA AI endpoint you are using. This parameter is used to identify the specific endpoint for usage tracking. Model name. The name of the model being used within the NVIDIA AI endpoint. This information helps you identify which model is contributing to the usage. Request headers. The headers sent with the request to the NVIDIA AI endpoint. These headers can provide valuable contextual information about the request, such as the user ID, the application ID, or other relevant data. Request body. The body of the request sent to the NVIDIA AI endpoint. This typically contains the input data for the model. Response headers. The headers returned by the NVIDIA AI endpoint in the response. These headers can provide additional insights into the request's execution, such as latency, resource usage, or error codes. Response body. The content of the response returned by the NVIDIA AI endpoint. This is usually the output generated by the model based on the input data. Outputs. Usage metrics. This callback function gathers and returns usage metrics, such as the number of requests sent to the endpoint, the total amount of data processed, the average response time, and the cost incurred for using the endpoint. Steps. Capture request information. The get usage callback function collects information about the request, including the endpoint name, model name, request headers, and request body. Track usage metrics. It tracks and accumulates usage metrics based on the captured information. This can involve counting the number of requests, calculating the amount of data processed, and measuring the response time for each request. Log and/or store data. The collected data can be logged to a file, stored in a database, or processed in other ways for further analysis or monitoring. Metrics. Request count. The number of requests sent to the endpoint. Data processed. The total amount of data sent to the endpoint for processing. Average response time. The average time it takes for the endpoint to process a request and return a response. Endpoint cost. The cost incurred for using the endpoint. Visualization plots. Request count vs. time. A line chart showing the number of requests sent over time. Data processed vs. time. A line chart showing the amount of data processed over time. Average response time vs. time. A line chart showing the average response time over time. Endpoint cost vs. time. A line chart showing the cost incurred over time. Challenges and fixes. Challenge 1. Incomplete information. The get usage callback might not always have access to all the required information, such as the model name or the cost incurred for specific requests. Sample use case. The NVidia AI endpoint might not return enough information about the model being used or the cost incurred. Fixes. Implement custom logic. You can implement custom logic within the callback function to infer missing information based on available data or other sources. Use additional tools. Consider using tools like cloud monitoring services or other data collection mechanisms to gather more complete usage information. Challenge 2. Data storage and analysis. Storing and analyzing the collected usage data effectively can be challenging, especially when dealing with large volumes of information. Sample use case. Storing usage data in a database might lead to performance issues, or analyzing the data might require complex tools or algorithms. Fixes. Optimize data storage. Use appropriate data storage methods and database technologies that can efficiently handle large datasets. Leverage data analysis tools. Utilize data analysis tools and techniques to extract insights from the collected usage data. Challenge 3. Security considerations. Ensuring the security of the collected usage data is crucial, particularly if it contains sensitive information. Sample use case. The collected usage data might include user IDs or other confidential data that needs to be protected. Fixes. Implement data encryption. Encrypt the usage data at rest and in transit to prevent unauthorized access. Control access. Restrict access to the collected usage data to authorized personnel. Follow security best practices. Adhere to security best practices for data collection, storage, and handling. NVidia AI endpoints callbacks. Standardize model name. Description. The standardized model name callback is designed to ensure model names are consistent and usable within LangChain. It modifies model names based on the specified format to avoid errors or inconsistencies in the pipeline. Inputs. Model name. The original name of the model, typically provided by the user or retrieved from an external source. Outputs. Standardized model name. The processed model name that is consistent with the defined format. Steps. Retrieve the original model name. Replace spaces with underscores. Convert the name to lowercase. If the name includes a version, separate the version from the base model name and keep only the base name. Metrics. Consistency of model names across different pipelines. Visualization plots. Fine-tune parameters. Uncertainty methods. Challenges and fixes. Challenge 1. Incorrect model names leading to errors. Sample use case that resulted in challenge 1. A model name with spaces or uppercase letters could cause errors when interacting with the model. Fixes to challenge 1. Standardizing the model name by replacing spaces with underscores and converting to lowercase ensures compatibility with LangChain and other tools. Challenge 2. Versioned model names causing confusion or errors. Sample use case that resulted in challenge 2. If a model name includes a version, it might not be compatible with certain tools or lead to ambiguity. Fixes to challenge 2. Separating the base model name from the version helps maintain consistency and avoid potential issues. LangChain NVidia AI endpoints chat models. Description: explain in detail the LangChain NVidia AI endpoints chat models leverage the power of NVIDIA's AI infrastructure to offer high-performance, scalable, and efficient chatbot solutions. This integration facilitates seamless integration of NVIDIA's cutting-edge AI models into LangChain applications, enabling users to access and utilize these models directly within their LangChain workflows. Inputs. Input 1. Explain in detail textual input, which can be user prompts, questions, or any other text-based data. Input 2. Explain in detail contextual information, which can include previous interactions, relevant documents, or other background knowledge. Outputs. Output 1. Explain in detail a generated text response, which can be an answer to a question, a summary of a document, or a creative text composition. Output 2. Explain in detail confidence scores, indicating the model's level of certainty in its generated response. Steps. Step 1. Explain in detail the user interacts with the LangChain application, providing input prompts or questions. Step 2. Explain in detail LangChain processes the input and sends it to the chosen NVidia AI endpoint chat model. Step 3. Explain in detail the NVidia AI endpoint model processes the input and generates a text response. Step 4. Explain in detail LangChain receives the response from the NVidia AI endpoint model and presents it to the user. Metrics. Metric 1. Explain in detail accuracy, which measures the correctness of the model's responses based on predefined evaluation metrics. Metric 2. Explain in detail fluency, which evaluates the quality and coherence of the generated text. Visualization plots. Visualization plot 1. Explain in detail confusion matrices, which visualize the model's performance by showing the distribution of predicted and actual classes. Visualization plot 2. Explain in detail attention heat maps, which highlight the attention weights assigned to different words in the input sequence. Fine-tune parameters. Parameter 1. Explain in detail learning rate, which controls the step size during model training. Parameter 2. Explain in detail batch size, which determines the number of data samples used in each training iteration. Uncertainty methods. Uncertainty method 1. Explain in detail dropout-based uncertainty estimation, which introduces randomness in the model's predictions during inference. Uncertainty method 2. Explain in detail Bayesian neural networks, which provide a probabilistic framework for modeling uncertainty. Challenges and fixes. Challenge 1. Explain in detail high latency issues when communicating with the NVidia AI endpoints. Sample use case that resulted in challenge 1 during real-time chat conversations. Delays in model responses due to network latency can impact user experience. Fixes to challenge 1. Employing caching mechanisms to store frequently used responses, optimizing network infrastructure for low latency, and implementing asynchronous communication strategies. Challenge 2. Explain in detail limited access to specific NVIDIA AI models for certain users. Sample use case that resulted in Challenge 2. A researcher might require access to a specialized model not available through the public API. Fixes to Challenge 2. Providing access to a wider range of NVIDIA AI models through a subscription-based service or collaborating with NVIDIA to expand model availability. Challenge 3. Explain in detail the need for robust error handling mechanisms when communicating with the NVIDIA AI endpoints. Sample use case that resulted in Challenge 3. A network outage or service interruption can cause the model to fail to respond. Fixes to Challenge 3. Implementing error handling mechanisms in LangChain to gracefully handle network issues and provide feedback to the user. LangChain NVIDIA AI endpoints chat models. Chat NVIDIA. Description: the Chat NVIDIA model is a large language model LLM specifically designed for conversational AI applications. It's part of the LangChain ecosystem and allows you to utilize the power of NVIDIA's AI platform for natural language understanding and generation. The model excels at tasks like generating creative text formats, translating languages, writing different kinds of creative content, and answering your questions in an informative way. Inputs. Prompt: the user's input. A textual query or statement that triggers the model to generate a response. The prompt can be anything from a simple question to a complex command or request. Outputs. Response: the Chat NVIDIA model's output. A generated text response that is relevant to the provided prompt. It attempts to understand the intent of the input and provide a coherent and contextually appropriate answer. Steps. The input prompt is sent to the Chat NVIDIA model. The model processes the prompt and generates a response based on its training data and understanding of language. The response is returned to the user. Metrics. Accuracy: the ability of the model to provide correct and relevant information in response to various prompts. Fluency: the smoothness and naturalness of the generated text, ensuring that the output reads like human written language. Coherence: the logical consistency and flow of the generated text, making sure the response makes sense in its entirety. Visualization plots. Attention visualization: visualizing the model's attention weights during text generation can help understand which parts of the input are most influential in shaping the output. Embedding space visualization: mapping words and phrases from the input and output into a multidimensional space can reveal relationships and patterns in the model's understanding. Fine-tune parameters. Learning rate controls the step size taken during the model's training process. Batch size determines the number of training examples used in each iteration of the models. Training. Epochs: number of times the model is trained on the entire dataset. Uncertainty methods. Temperature scaling: adjusting the model's output probability distribution to control the level of randomness and creativity in the response. Ensemble predictions: combining the outputs of multiple Chat NVIDIA models to improve robustness and reduce uncertainty. Challenges and fixes. Challenge 1: generating factually inaccurate or biased information. Sample use case that resulted in Challenge 1: a prompt asking for historical information might produce an answer containing incorrect details or perpetuating historical biases. Fixes to Challenge 1. Utilize models trained on high-quality datasets known for their factual accuracy. Implement fact-checking mechanisms to verify information generated by the model. Challenge 2: providing responses that lack creativity or originality. Sample use case that resulted in Challenge 2: a prompt requesting a short story might result in a generic and predictable narrative. Fixes to Challenge 2. Fine-tune the model on a dataset rich in creative text formats. Experiment with different temperature scaling values to encourage more diverse and imaginative outputs. Challenge 3 difficulty in handling complex or nuanced queries. Sample use case that resulted in challenge 3 a prompt requiring logical reasoning or understanding of multiple concepts might lead to an incomplete or incorrect response. Fixes to challenge 3. Leverage techniques like chain of thought prompting, where the model is encouraged to break down complex tasks into smaller steps. Utilize knowledge-enhanced models that have access to external knowledge bases. Challenge 4 generating outputs that are offensive or inappropriate. Sample use case that resulted in challenge 4 a prompt containing sensitive or offensive language might result in a response that perpetuates harmful stereotypes or biases. Fixes to challenge 4. Train the model on datasets that are diverse, inclusive, and free from harmful content. Implement safety mechanisms to filter out inappropriate or offensive language in the generated output. NVidia AI endpoints embeddings. Description: the NVidia AI endpoints embeddings module provides a way to leverage NVIDIA AI endpoints for embedding generation. NVIDIA AI endpoints are a service that allows users to deploy and run custom models, including embedding models, in the cloud. By using this module, users can easily access and utilize these pre-trained or custom embedding models for various NLP tasks like semantic search, question answering, and text summarization. Inputs. Text: the input text that needs to be converted into an embedding vector. This can be a single sentence, a paragraph, or a longer document. Outputs. Embedding vector: a numerical representation of the input text, where each dimension of the vector represents a specific semantic feature of the text. Steps. Text preprocessing: the input text is first preprocessed, which might involve tasks like tokenization, lower casing, and removing stop words. Embedding generation: the preprocessed text is then passed to the selected NVIDIA AI endpoint embedding model, which generates a numerical embedding vector representing the text's meaning. Metrics. Cosine similarity: this metric is commonly used to measure the similarity between two embedding vectors. It ranges from 0 to 1, where 1 represents perfect similarity and 0 represents no similarity. Visualization plots. Embedding visualization: this plot shows the embedding vectors of different texts in a low-dimensional space, allowing users to visualize the relationships between different texts. Fine-tune parameters. Model selection: users can choose from a variety of pre-trained embedding models available on NVIDIA AI endpoints or even fine-tune their own models for specific domains or tasks. Batch size: this parameter determines the number of texts processed simultaneously by the embedding model, which can impact the speed and memory usage. Uncertainty methods. Confidence scores: some embedding models may provide confidence scores for each dimension of the generated embedding vector, indicating the model's confidence in the assigned values. Challenges and fixes. Challenge 1: handling long texts. When dealing with very long texts, generating embeddings can be computationally expensive and might exceed memory limitations. Sample use case that resulted in challenge 1: trying to generate embeddings for a large document containing thousands of words. Fixes to challenge 1. Chunking: divide the long text into smaller chunks and generate embeddings for each chunk individually. Sentence embedding: use a sentence-level embedding model that can handle longer sequences more efficiently. Challenge 2: model selection and optimization. Choosing the right embedding model for a specific task can be challenging, and optimizing model parameters can be time-consuming. Sample use case that resulted in challenge 2 using a general-purpose embedding model for a highly specialized domain, resulting in suboptimal performance. Fixes to challenge 2. Domain-specific models. Explore and experiment with domain-specific embedding models pre-trained on datasets relevant to your task. Fine-tuning. Fine-tune a pre-trained model on a smaller dataset specific to your task. Hyperparameter tuning. Optimize hyperparameters like batch size and learning rate to improve model performance. NVidia AI endpoints. ImageGAN. Description: the ImageGAN endpoint in LangChain NVidia AI endpoints leverages the power of stable diffusion models to generate images based on textual prompts. It provides a versatile tool for creative tasks, allowing users to translate their descriptions into visual representations. Inputs. Prompt a textual description of the image to be generated. This input serves as the foundation for the image creation process, guiding the model's understanding of the desired output. Parameters. Optional parameters that can be used to fine-tune the image generation process. These parameters can include aspects such as image resolution, aspect ratio, and artistic style, enabling users to tailor the output to their specific needs. Outputs. Image. The generated image based on the provided prompt and parameters. This output represents the visual interpretation of the textual input, embodying the model's understanding of the description. Metadata. Information about the generated image, including details such as image size, resolution, and potentially other relevant metadata. Steps. Textual prompt processing. The provided prompt is processed and analyzed to extract key concepts, entities, and stylistic preferences. This step involves understanding the user's intent and translating it into a format suitable for the image generation model. Model inference. The processed prompt is then fed into the stable diffusion model. The model utilizes its training data and internal mechanisms to generate a series of images based on the provided input. Output processing. The generated images are then post-processed, potentially including steps such as image resizing, quality enhancement, and format conversion. Metrics. Image quality evaluates the visual quality of the generated images, considering factors such as clarity, detail, and artistic appeal. This metric helps gauge the model's ability to effectively translate textual input into visually pleasing outputs. Fidelity to prompt measures the extent to which the generated image aligns with the provided prompt. This metric assesses the model's accuracy in interpreting and translating the user's intent into a visual representation. Diversity evaluates the diversity of images generated for a given prompt. This metric explores the model's ability to produce variations and explore different interpretations of the provided textual input. Visualization plots. Image grids. Visualizing generated images for different prompts or parameter combinations, allowing users to quickly compare and analyze the model's output. Image embeddings. Visualizing the latent representations of generated images, potentially revealing underlying patterns and relationships between different outputs. Fine-tune parameters. Image resolution controls the size of the generated images, influencing the level of detail and visual complexity. Aspect ratio determines the width to height ratio of the generated images, allowing users to tailor the image's dimensions to their specific requirements. Artistic style influences the overall visual style of the generated images, enabling users to select a specific artistic aesthetic such as realism, impressionism, or abstract art. Sampling steps determines the number of steps the model takes during the image generation process. potentially influencing the image's quality and complexity. Uncertainty methods. Ensemble predictions generating multiple images from different models or different instances of the same model, allowing users to evaluate the consistency and variability of the output. Saliency maps highlighting regions of the generated images that are most important for the model's decision-making process, potentially providing insights into the model's reasoning and decision-making process. Challenges and fixes. Challenge 1: ambiguous or inconsistent prompts. If the provided prompt is ambiguous or lacks clear instructions, the model might struggle to generate coherent and relevant images. Sample use case: a prompt like a beautiful landscape could lead to highly variable outputs based on the user's subjective understanding of beautiful. Fixes. Providing more specific details and context in the prompt, such as describing the desired landscape features, colors, and mood. Utilizing prompt engineering techniques to clarify the intended meaning and ensure consistency in the prompt's wording. Challenge 2: overly complex prompts. Highly complex or detailed prompts can potentially overwhelm the model, leading to unexpected or inconsistent outputs. Sample use case: a prompt requesting an image depicting a complex scene with multiple objects, characters, and intricate details might result in a confusing or incomplete image. Fixes. Breaking down the prompt into smaller, more manageable parts, focusing on generating individual elements before combining them. Experimenting with different prompt formats and structuring the prompt in a way that is more easily processed by the model. Challenge 3: limited training data. The model's ability to generate images is limited by the specific data it was trained on. This can lead to limitations in the diversity and quality of the generated images. Sample use case: the model might struggle to generate images with specific textures, objects, or scenes that were not adequately represented in its training data. Fixes. Exploring specialized image generation models that have been trained on specific datasets relevant to the desired output. Utilizing fine-tuning techniques to adapt the model's capabilities to specific domains or styles of imagery. Challenge 4: technical limitations. The computational requirements of image generation can lead to limitations in the speed and efficiency of the process. Sample use case: generating high-resolution images or performing complex image manipulations might require significant computational resources, potentially resulting in longer processing times. Fixes. Exploring alternative hardware configurations with more powerful GPUs or specialized processing units. Utilizing techniques to optimize the image generation process, such as reducing the number of sampling steps or employing efficient model architectures. Challenge 5: ethical considerations. Generated images might reflect biases or stereotypes present in the model's training data, potentially leading to problematic or offensive outputs. Sample use case: a prompt requesting an image of a doctor might disproportionately generate images of male individuals due to historical biases in medical professions. Fixes. Carefully evaluating and mitigating biases in the model's training data. Implementing mechanisms to monitor and control the model's output, ensuring it aligns with ethical guidelines and avoids generating harmful or offensive content. NVidia AI endpoints. ImageGen image NVidia. Description: the image NVidia class utilizes the NVidia AI endpoints service to generate images based on text prompts. It allows users to leverage the power of NVIDIA's cutting-edge image generation models for various creative and practical applications. Inputs. Prompt: a text description or a set of instructions that describes the desired image. The prompt should be clear, concise, and provide specific details about the subject, style, composition, and other relevant aspects of the desired image. Model name: the name of the NVidia AI endpoint's image generation model to use. You can find a list of available models and their capabilities on the NVidia AI endpoints. Documentation. Outputs. Image: the generated image in a format specified by the model, typically as a binary stream or a URL. Steps. The user provides a text prompt describing the desired image and the name of the NVidia AI endpoint's image generation model to use. The NVidia class sends the prompt and model name to the NVidia AI endpoint service. The service processes the prompt and uses the selected model to generate an image based on the prompt's instructions. The generated image is returned to the user. Metrics. FID Shay inception distance, a metric that measures the similarity between the generated images and real images from a specific dataset. A lower FID score indicates better image quality and fidelity. Is inception score a metric that evaluates the diversity and quality of generated images? A higher IS score indicates greater diversity and more realistic images. Visualization plots. Visualizations of generated images for various prompts to showcase the model's capabilities and understand its strengths and weaknesses. Comparison plots of generated images using different models or different parameters of the same model to analyze the impact of model choice or parameter tuning. Fine-tune parameters. Image size: the desired resolution of the generated image. Higher resolutions can produce more detailed and visually appealing images, but they also require more computational resources. NUM inference steps: the number of steps the model takes to generate the image. More steps can lead to more detailed images but also increase generation time. Uncertainty methods. Confidence scores for individual pixels in the generated image, indicating the model's uncertainty about the generated content. Probabilistic image generation, where the model outputs a distribution over possible image pixels instead of a single deterministic image. Challenges and fixes. Challenge 1: the generated image may not accurately reflect the prompt's instructions, leading to unexpected or inaccurate results. Sample use case that resulted in challenge 1: a user prompts the model to generate an image of a sunset over a beach, but the generated image lacks specific features like palm trees or waves, leading to a lack of context. Fixes to challenge 1. Refine the prompt by providing more specific details about the desired image, including specific features, composition, colors, and styles. Experiment with different model parameters like image resolution and NUM inference steps to fine-tune the generation process. Explore different NVidia AI endpoints image generation models, as each model may have its own strengths and weaknesses in capturing specific details or artistic styles. Challenge 2: the generated image might exhibit visual artifacts or noise, particularly when dealing with complex prompts or high resolutions. Sample use case that resulted in challenge 2: a prompt to generate a detailed image of a cityscape with intricate architectural details might lead to blurry areas or uneven textures in the generated image. Fixes to challenge 2. Increase the NUM inference steps to allow the model more time to refine the image and reduce noise. Use a higher resolution model to produce more detailed images, but be aware of the increased computational cost. Experiment with different image generation models that might have better noise reduction capabilities or specific strengths in handling complex scenes. Consider post-processing techniques to improve the visual quality of the generated image. such as noise reduction algorithms or image sharpening filters. NVidia AI endpoints ImageGAN image parser. Description: the image parser class is designed to process image data and convert it into a format suitable for use with language models. It leverages the image generation capabilities of the NVidia AI endpoint service. Inputs: image, a file path to the image or an image object. The image must be in a supported format like JPEG, PNG, or GIF. Outputs: text embedding, a text embedding representation of the image. The embedding is generated by processing the image through the image generation model. Imager L, the URL of the generated image. This allows you to access and visualize the generated image. Steps: the image is sent to the NVidia AI endpoints image generation service. The service generates a new image based on the input image. The generated image is processed to extract the textual embedding. Metrics: image similarity. The similarity between the input image and the generated image can be evaluated using metrics like SSIM or PSNR. Text embedding quality: the quality of the text embedding can be evaluated based on its ability to accurately represent the image content. Visualization plots: image comparison plot. This plot shows the input image and the generated image side by side, allowing for visual comparison. Embedding visualization: the text embedding can be visualized using methods like tsna or UMAP to understand its structure and relationships. Fine-tune parameters: model name, the name of the specific image generation model to use. Prompt: a text prompt that can be used to influence the image generation process. Resolution: the desired resolution of the generated image. Uncertainty methods: confidence scores: the image generation model can provide confidence scores for different parts of the generated image, indicating the model's uncertainty in its predictions. Ensemble methods: multiple image generation models can be used together to generate multiple images. The variations between these images can be used to estimate uncertainty. Challenges and fixes. Challenge 1: the generated image may not be accurate or representative of the input image. Sample use case that resulted in challenge 1: an input image of a dog was processed, but the generated image showed a cat instead. Fixes to challenge 1: experiment with different image generation models to find one that is better suited for the specific task. Provide a more specific or detailed prompt to guide the image generation process. Increase the resolution of the generated image to potentially improve the accuracy of the generated image. Challenge 2: the text embedding may not accurately capture the semantic content of the image. Sample use case that resulted in challenge 2: an image of a sunset was processed, but the text embedding did not contain words related to the sunset, like sun or sky. Fixes to challenge 2: fine-tune the text embedding model on a dataset of image-text pairs that are relevant to the specific domain. Explore different text embedding techniques and algorithms to find one that performs better for the given image data. Consider using a multimodal model that can jointly process image and text data for a more accurate representation of the image content. NVidia AI endpoints LLM. Description: the NVidia AI endpoints LLM leverages NVIDIA's AI platform to provide access to a variety of powerful language models. This approach offers several benefits, including high performance. Utilizing NVIDIA's hardware and infrastructure ensures efficient processing and fast response times. Scalability: the platform is designed to handle large-scale language modeling tasks. Security: NVIDIA's platform provides a secure environment for sensitive data. Ease of use. LangChain simplifies the integration of these models into applications. Inputs. Text. The input text that the model will process. This can be a single sentence, paragraph, or longer document. Outputs. Text. The model's generated response to the input text. This could be a summary, translation, or other relevant output depending on the specific model and task. Steps. Initialization. The LangChain framework is initialized and configured to connect with the NVidia AI platform. Model selection. A specific language model is chosen based on the requirements of the task, e.g., translation, summarization, question answering. Input processing. The input text is pre-processed to prepare it for the selected model. Model execution. The selected model is invoked with the pre-processed input text. Output processing. The model's generated output is post-processed to format it appropriately for the application. Metrics. Accuracy measures how well the model's output aligns with the desired results for a given task. Latency measures the time taken for the model to generate a response, which is crucial for real-time applications. Cost monitors the cost of using the NVIDIA AI platform for model execution. Visualization plots. Model performance over time. A plot showing the accuracy and latency of the model over time, which can highlight potential performance improvements or degradation. Model usage patterns. A plot visualizing the frequency of different model calls and pay. Distribution of input text lengths, which can help identify areas for optimization. Fine-tune parameters. Learning rate controls the speed at which the model adjusts its parameters during training. Batch size determines the number of examples used for each training step, affecting the model's training speed and memory consumption. Number of epochs specifies the number of times the entire training dataset is used to adjust the model's parameters, impacting the model's training duration. Uncertainty methods. Monte Carlo dropout. A technique used to estimate the model's uncertainty by introducing randomness during inference, providing insights into the model's confidence in its predictions. Temperature scaling. A method that adjusts the probability distribution of the model's output tokens, influencing the model's confidence and risk-taking behavior. Challenges and fixes. Challenge 1. High latency for complex tasks. Sample use case that resulted in Challenge 1. A user requests a detailed analysis of a lengthy document, leading to a significant delay in the model's response. Fixes to Challenge 1. Optimize model selection. Choose a model best suited for complex tasks with a balance of accuracy and efficiency. Utilize GPU acceleration. Leverage NVIDIA GPUs for accelerated processing to reduce latency. Pre-process text. Break down lengthy input text into smaller chunks to facilitate faster processing. Challenge 2. Cost optimization for frequent usage. Sample use case that resulted in Challenge 2. A high-traffic application requires frequent model calls, leading to high computational costs. Fixes to Challenge 2. Batching requests. Combine multiple requests together to reduce the number of individual model calls. Model caching. Cache frequently used model responses to avoid redundant computations. Efficient model selection. Choose a model with an optimal trade-off between accuracy and cost. LangChain NVIDIA AI Endpoints LLM NVIDIA. Description. The LangChain NVIDIA AI Endpoints LLM is a wrapper for NVIDIA's AI inference service is, allowing LangChain users to easily access and utilize NVIDIA's powerful pre-trained language models. It provides a convenient way to interact with these models through the LangChain framework, facilitating various natural language processing tasks. Inputs. Input 1. Text prompt. the text input provided to the LLM. Defining the task or question the user wants to be addressed. Input to model name specifies the name of the NVidia AI inference service model to be used for processing the input. Outputs. Output 1 generated text, the text response produced by the LLM based on the input prompt and the selected model. Output 2 metadata, information regarding the model used, including its version and other relevant parameters. Steps. Step 1. Initialize the LangChain interface. Create an instance of the LangChain interface, configuring it to connect to the NVidia AI inference service. Step 2. Send the input prompt. Submit the user's text input to the initialized LangChain interface, along with the selected model name. Step 3. Receive the response. Receive the generated text output from the LLM, along with metadata about the model and processing details. Metrics. Metric 1. Latency measures the time taken for the LLM to process the input and generate the output, reflecting the model's speed. Metric 2. Accuracy assesses the quality of the LLM's output by comparing it to a ground truth or evaluating its performance against specific criteria. Visualization plots. Visualization plot 1. Latency distribution, a plot showing the distribution of latency values for different input prompts or models, allowing for performance analysis. Visualization plot 2. Accuracy comparison, a plot comparing the accuracy of different NVIDIA models for a specific task or set of prompts. Fine-tune parameters. Parameter 1. Model version allows for selecting a specific version of the NVIDIA model to use, enabling customization based on performance or feature availability. Parameter 2. Runtime configuration provides options for fine-tuning the runtime environment of the model, potentially including resource allocation or optimization settings. Uncertainty methods. Uncertainty method 1. Ensemble methods, combining multiple NVIDIA models to provide more robust predictions and reduce uncertainty in the generated text. Uncertainty method 2. Confidence scores, utilizing internal confidence scores generated by the LLM to indicate the certainty of the output and identify potential areas of uncertainty. Challenges and fixes. Challenge 1. API connection issues, difficulties connecting to the NVIDIA AI inference service. API, potentially due to network issues or incorrect configurations. Sample use case. The user attempts to access the service, but receives error messages related to network connectivity. Fixes. Check network connectivity, ensure proper firewall rules are in place, and verify the API endpoint details. Challenge 2. Model selection, choosing the appropriate NVIDIA model for a specific task, considering factors like model size, accuracy, and computational resources. Sample use case. The user tries to use a model that is not suitable for the desired task, resulting in subpar output or resource limitations. Fixes. Research and explore available NVIDIA models to identify the best fit for the task, considering relevant benchmarks or documentation. LangChain NVIDIA AI endpoints re-ranking. Description. Re-ranking is a technique used to improve the quality of search results by reordering them based on their relevance to a query. In the context of LangChain and NVIDIA AI endpoints, re-ranking can be used to refine the output of a language model, ensuring that the most relevant and accurate responses are presented to the user. Inputs. Query. The user's input, which is used to trigger the search or retrieval of information. Initial retrieval results a list of documents or responses retrieved from a knowledge base or language model, typically ranked based on basic similarity or retrieval scores. Outputs. Re-ranked results, a reordered list of retrieval results, where the most relevant results are placed at the top. Re-ranking score, a score associated with each result that indicates its relevance to the query. Steps. Initial retrieval. The query is sent to a knowledge base or language model, which retrieves a set of documents or responses based on its internal knowledge and ranking. Algorithms. Re-ranking. A dedicated re-ranking model, e.g., a neural network, is used to evaluate the relevance of the initial results to the query. The re-ranking model takes the query and the initial results as input and produces a new ranking, based on factors such as semantic similarity, contextual understanding, and user preferences. Metrics. Mean average precision map, a measure of the average precision across multiple queries, indicating the accuracy of the re-ranking model in placing relevant results at the top. Normalized discounted cumulative gain, NDCG, a measure that considers the ranking position of relevant results, penalizing those that are placed lower in the ranking. Visualization plots. Precision recall curve plots the precision of the re-ranking model against the recall, showing its ability to retrieve relevant results while minimizing irrelevant ones. Ranking distribution visualizes the distribution of results in the initial and re-ranked lists, highlighting the impact of re-ranking on the overall ranking quality. Fine-tune parameters. Learning rate controls the speed at which the re-ranking model learns from the training data. Embedding dimension determines the size of the vector representations used to capture the semantic meaning of the query and documents. Number of layers influences the complexity of the re-ranking model, allowing for deeper analysis of the input data. Uncertainty methods. Confidence scores provides an estimate of the re-ranking model's confidence in its predictions, allowing for a more nuanced interpretation of the re-ranked results. Ensemble methods combine predictions from multiple re-ranking models to reduce uncertainty and improve the overall robustness of the system. Challenges and fixes. Challenge 1. Lack of training data. Sample use case. The re-ranking model performs poorly because it lacks sufficient examples of relevant and irrelevant results. Fixes. Augmenting existing data, expanding the training dataset by adding synthetic examples or manually labeling existing results. Transfer learning, leveraging pre-trained language models or re-ranking models trained on similar tasks to improve initial performance. Challenge 2. Cold start. Sample use case. The re-ranking model struggles to provide meaningful results for queries that are significantly different from those it has been trained on. Fixes. Hybrid approaches, combining basic similarity-based ranking with re-ranking to handle unseen queries effectively. Dynamic learning, continuously updating the re-ranking model with new data to adapt to changing query patterns. Langchan NVidia I endpoints re-ranking. NVidia re-rank. Description. The NVidia re-rank tool provides a method for re-ranking search results based on their relevance to the user's query. This is achieved through a process of rescoring the initial search results using a pre-trained deep learning model. Inputs. Query. The user's search query, which will be used to find relevant documents. Initial results. A list of documents retrieved from an initial search. Outputs. Re-ranked results. A list of documents ordered by their relevance to the query, as determined by the re-ranking model. Steps. The NVidia re-rank tool first takes the user's query and the list of initial search results as input. It then uses a pre-trained deep learning model to rescore the initial results based on their relevance to the query. Finally, it returns the re-ranked results, ordered by their relevance scores. Metrics. Mean average precision map, a measure of the average precision of the re-ranking model over a set of queries. Normalized discounted cumulative gain (NDCG), a measure of the ranking quality of the re-ranked results, taking into account the position of relevant documents in the ranking. Visualization plots. Precision recall curve. This plot shows the trade-off between precision and recall for different ranking thresholds. Rank relevance plot. This plot shows the relevance score of each document in the ranking, allowing you to visualize how well the model is able to rank relevant documents higher. Fine-tune parameters. Learning rate controls the step size used during model training. Batch size controls the number of samples used in each training iteration. Epochs, the number of times the entire training dataset is used to train the model. Uncertainty methods. Confidence score. The NVidia re-rank tool can provide a confidence score for each document in the re-ranked results. This score can be used to indicate the model's certainty in the ranking of a particular document. Entropy. The entropy of the model's prediction can be used as a measure of uncertainty. A higher entropy value indicates greater uncertainty. Challenges and fixes. Challenge 1. The model may not be able to effectively re-rank documents that are very similar in content. Sample use case. 2 documents with nearly identical content but different titles may be ranked poorly by the model if the title is the only distinguishing feature. Fixes to challenge 1. Fine-tune the model on a dataset of similar documents to improve its ability to distinguish between them. Challenge 2. The model may be biased towards certain types of documents. Sample use case. If the training data is heavily skewed towards news articles, the model may be more likely to rank news articles higher than other types of documents, even if the query is more relevant to a different document type. Fixes to challenge 2. Use a more diverse dataset for training the model. You can also add features to the model that represent the document type, which can help it to learn to rank documents more fairly. NVidia AI endpoints re-ranking ranking. Description. The NVidia AI endpoints re-ranking functionality enhances the ranking of retrieved documents by leveraging NVidia AI endpoints, specifically the re-ranking endpoint. This endpoint utilizes a powerful language model to re-evaluate the relevance of documents based on a provided query. The re-ranking process improves the accuracy and relevance of document retrieval by considering semantic understanding and contextual relationships. Inputs. Query. The user's search query or question, providing the context for re-ranking. Documents. A list of documents retrieved from an initial search or other source. These documents are candidates for re-ranking. Outputs. Re-ranked documents. A reordered list of documents based on their relevance to the query, as determined by the re-ranking endpoint. Ranking scores. A set of scores associated with each document, indicating the relative relevance of each document to the query. These scores can help in further analysis and decision-making. Steps. Document retrieval. Initially, a set of documents are retrieved based on a query, using techniques like keyword matching, TF-IDF, or other search methods. Re-ranking endpoint call. The retrieved documents are sent to the NVidia AI endpoint's re-ranking endpoint, along with the query. Re-ranking evaluation. The language model at the endpoint processes the query and documents, evaluating their semantic relationships and relevance. Reordering. The endpoint returns a reordered list of documents based on their evaluated relevance, with the most relevant documents appearing first. Metrics. MRR. Mean reciprocal rank measures the average rank of the most relevant document. Higher MRR indicates better ranking accuracy. NDCG. Normalized discounted cumulative gain considers the relevance and position of documents giving higher weight to highly relevant documents appearing early in the ranking. Visualization plots. Ranking distribution. A plot showing the distribution of ranking scores for the retrieved documents. Top K re-ranking performance. A plot comparing the accuracy of re-ranking for different values of K. Number of top-ranked documents. Fine-tune parameters. Threshold. The minimum score required for a document to be considered relevant during re-ranking. This parameter influences the overall level of strictness in the ranking process. Re-ranking model. Different language models can be used for re-ranking. Fine-tuning specific parameters within these models can enhance their performance for particular domains or tasks. Uncertainty methods. Confidence scores. The re-ranking endpoint can provide confidence scores associated with each document's ranking. These scores indicate the certainty of the model's assessment of relevance. Ensemble re-ranking. Combining the outputs of multiple re-ranking models can provide more robust and reliable ranking results. Challenges and fixes. Challenge 1. Handling long documents. Long documents can pose a challenge for re-ranking models, as they may contain too much information to be fully processed effectively. Sample use case that resulted in challenge 1. A user searches for information on machine learning algorithms and retrieves a lengthy research paper containing various algorithms and their details. Re-ranking may struggle to accurately identify the most relevant sections within this document. Fixes to challenge 1. Document summarization before re-ranking. A summarization technique can be applied to reduce the length of documents, allowing the model to focus on the most important information. Chunking. Large documents can be broken down into smaller chunks, each of which can be re-ranked individually. Challenge 2. Domain specificity. Re-ranking models may struggle to effectively rank documents in highly specialized domains where domain-specific terminology and concepts are prevalent. Sample use case that resulted in challenge 2. A user in the medical field searches for information on a specific disease. The re-ranking model may not accurately identify relevant medical articles due to lack of domain knowledge. Fixes to challenge 2. Domain-specific fine-tuning. Training the re-ranking model on a data set from the specific domain can improve its performance in understanding and ranking relevant documents. Hybrid approaches. Combining re-ranking with other methods, such as keyword matching, that are more suited for specific domains can provide a more comprehensive ranking solution. NVidia AI endpoints tools. Description. The NVidia AI endpoints tools provide a powerful way to leverage NVIDIA's AI platform for language tasks within LangChain. These tools allow you to easily connect your LangChain applications to NVIDIA's AI endpoints, enabling access to a wide range of advanced models and capabilities for tasks like text generation, summarization, translation, and more. Inputs. Endpoint URL. The URL of the NVIDIA AI endpoint you want to connect to. A PI key or API key for accessing the endpoint obtained from the NVIDIA AI platform. Model name. The name of the specific model you wish to utilize from the endpoint, e.g. Text DaVinci 003 for GPT-3. Input text. The text you want to provide as input to the model. Outputs. Response text. The text generated by the model based on your input. Model metadata. Metadata related to the model, e.g. version, description, steps. Initialize a LangChain tool with the NVidia AI endpoints package, providing the endpoint URL, API key, and model name. Send your input text to the tool using a method like tool run input text. The tool interacts with the NVIDIA AI endpoint, submits your request, and receives a response. The response is processed and returned as output text and metadata. Metrics. Latency, the time it takes for the endpoint to process your request and return a response. Model performance metrics specific to the chosen model, such as perplexity, accuracy, or BLEU score, depending on the task. Resource utilization metrics related to the computational resources consumed by the endpoint during processing. Visualization plots. Model output distribution histograms or visualizations depicting the distribution of output values generated by the model. Latency distribution plots showing the distribution of latency values for different requests. Fine-tune parameters. Temperature controls the randomness of the model's output. Higher values lead to more diverse and creative responses. Top K limits the number of potential next tokens considered by the model, influencing the generated text's coherence and diversity. Top similar to top, but instead of a fixed number of tokens, it considers a probability threshold, allowing more diverse options. Uncertainty methods. Confidence scores. The model can provide confidence scores for its outputs, indicating its certainty about the generated text. Ensemble methods utilizing multiple models or runs of the same model to assess the variability and uncertainty of predictions. Challenges and fixes. Challenge 1 API key errors. Sample use case that resulted in challenge 1, an incorrect API key was provided. Fixes to challenge 1: ensure you have the correct API key for your NVidia AI account. Double-check the key's format and validity. Challenge 2: endpoint connection issues. Sample use case that resulted in challenge 2: the endpoint URL is incorrect or the endpoint is temporarily unavailable. Fixes to challenge 2: verify the endpoint URL. Check the status of the endpoint on the NVIDIA AI platform. If the issue persists, contact NVIDIA support for assistance. Challenge 3: model limits or quotas. Sample use case that resulted in challenge 3: you have exceeded the usage limits for the chosen model, preventing further requests. Fixes to challenge 3: check your account's usage limits on the NVIDIA AI platform. Consider upgrading your plan or using a different model with lower usage costs. Challenge 4: incorrect input format. Sample use case that resulted in challenge 4: the input text provided to the model is in an invalid format, causing errors. Fixes to challenge 4: ensure the input text is in the expected format for the chosen model. Refer to the model's documentation for specific input requirements. LangChain NVidia AI Endpoints Tools Server Tools Mixin. Description: the Server Tools Mixin class is a powerful tool in LangChain's NVidia AI endpoints integration. It simplifies the process of interacting with NVIDIA Triton Inference Server, making it easier to deploy and use LangChain models in a production-ready environment. This mixin provides functionalities to manage and interact with the Triton server, allowing for seamless integration with the LangChain ecosystem. Inputs: Triton Inference Server Endpoint. This is the URL or IP address of your running Triton Inference server. Model name: this is the name of the LangChain model you wish to deploy on Triton, which will be used to identify the model within the server. Model configuration: this includes the details about the model, such as input and output shapes, data types, and other parameters required for inference. Outputs: model deployment on Triton. The Server Tools Mixin enables the deployment of your LangChain model onto Triton Inference Server, making it readily accessible for inference requests. Inference results: once the model is deployed, the mixin facilitates the sending of inference requests to the server and receives the corresponding inference results, which can be further processed within LangChain. Steps: Initialization. The mixin initializes with the provided Triton server endpoint and model details. Model deployment. The server tool's mixin sends the model configuration to the Triton server, initiating the deployment process. Inference request handling. When an inference request is received, the mixin sends it to the Triton server and handles the response, processing it as required by the application. Metrics. Latency measures the time taken by the Triton server to process and respond to each inference request. Throughput indicates the number of inference requests processed per unit of time, reflecting the server's performance. Resource utilization provides insights into the server's CPU, memory, and GPU usage during inference processing. Visualization plots. Latency distribution plot visualizes the spread of inference latencies, highlighting potential bottlenecks or performance variations. Throughput over time plot shows how the number of requests processed per unit time evolves over the duration of inference. Resource utilization plot displays the consumption of CPU, memory, and GPU resources during inference, revealing resource usage patterns. Fine-tune parameters. Batch size adjusts the number of inference requests processed in a single batch, impacting latency and throughput. Model configuration allows fine-tuning of the model's input and output shapes, data types, and other parameters to optimize for specific use cases. Uncertainty methods. Ensemble methods. Multiple models can be deployed on Triton to create an ensemble, enhancing robustness and reducing uncertainty in predictions. Bayesian inference. Integrating Bayesian methods with the deployed model can quantify the uncertainty associated with predictions. Challenges and fixes. Challenge 1. Model deployment failure. The model deployment may fail due to invalid configuration, insufficient resources, or network issues. Sample use case that resulted in challenge 1. Providing an incorrect model name or attempting to deploy a model that exceeds the server's capacity. Fixes to challenge 1. Verify the model configuration, ensure adequate resources are allocated, and address network connectivity issues. Challenge 2. Inference request timeout. Inference requests might time out if the server is overloaded or the model takes too long to process. Sample use case that resulted in challenge 2. Sending a large batch of inference requests to a heavily loaded server or using a computationally intensive model. Fixes to challenge 2. Optimize the model or increase the server's capacity. Consider adjusting the batch size or implementing mechanisms to handle timeouts gracefully. Challenge 3. Data type mismatch. The model might fail to process inference requests if the data types of inputs and outputs do not match the model's expectations. Sample use case that resulted in challenge 3. Sending data in a format that is different from the model's defined input or output types. Fixes to challenge 3. Ensure that the data types of inputs and outputs are consistent with the model's configuration. Use appropriate data transformations to convert the data to the required format. Challenge 4. Resource limitations. The server might not have sufficient resources CPU, memory, GPU to handle large inference requests or a high volume of requests. Sample use case that resulted in challenge 4. Attempting to process a large batch of requests on a server with limited resources. Fixes to challenge 4. Allocate more resources to the server, optimize the model for efficiency, or consider using a more powerful server. Challenge 5. Network connectivity issues. The connection between the LangChain application and the Triton server might be unstable or unavailable. Sample use case that resulted in challenge 5. The network connection between the client application and the server is interrupted or unreliable. Fixes to challenge 5 ensure a stable and reliable network connection. Implement mechanisms to retry requests or handle network errors gracefully.